So good afternoon. My name is Dr. Richardson. This is lecture 4 of the course entitled An Introduction to Linear Algebra Using Python. And my email address, srichards22@comcast.net, is listed below. And feel free to contact me if you have questions on the course content, problem sets, problem set solutions, lectures, typos, etc. So some of you are probably behind in terms of the course material. So I want to bring everybody up to speed on what's going on. First of all, the lectures are being video recorded. Note that learning is not a passive activity. Whether you look at the lectures in real time on Tuesday afternoons at 2 or look at the video clips, please, as you review these lectures, take notes. You're not going to learn anything by just simply watching me or listening to me perform. There are problem sets for the course and they're essential. Just by looking at the material, either in the video clips and not doing the problem sets, you're not going to get much out of this course. So you need practice, practice, practice in applying the concepts to exercises. Now, for all registered students, there currently are 4 problem sets posted on the Google Drive. Problem set 1, problem set 2, problem set 3, and actually problem set 4 was posted yesterday. The solution keys to problem sets 1, 2, and 3 are also posted. So I would make the following recommendation or set of recommendations if you're behind in the material. The course is based on, it builds from previous lectures. So the course is like building a house. You start from the foundation and work your way up. Problem set 4 is available, but if you haven't done the previous problems sets, I'd recommend starting with problem set 1. It turns out the very first problem on problem set 1 is probably the most difficult problem in the entire course. And I've actually given you guidelines how to do that first problem. So at least a third of it. So you can follow that, but skip around and do some problems in problem set 1. So you can make sure that you've mastered the concepts that are discussed in lecture 1. Then and only then go on to problem set 2 and then problem set 3. And eventually you'll catch up. In doing the problem sets, what you should not do is look at the solution key and work backwards. You'll learn nothing. What you should do is attempt to do a few problems and check your solutions. And you can cover the solution key with a piece of paper and slide down line by line to get hints on how to do a problem if you're stuck. But by taking the effort of going and looking at simple problems and then more moderately difficult problems and finally challenging problems, that's how you learn how all this works. Problem sets have 2 parts. There are analytical problems that you work in the first part, and solution keys are provided. And there are Python lab exercises, which really are self-study. I mean, it's a way for you to learn elements of Python, not the entire language. There are experts who tell me that they're learning new things about Python and they've worked on it for years. So we're just going to use some tools in Python to reinforce the ideas of linear algebra. This course is entitled An Introduction to Linear Algebra Using Python. It's not an introduction to Python using linear algebra. So the emphasis is at linear algebra, and we'll just use the tools of Python. You're encouraged to ask questions. So our lecture will begin today, it will end today at 3:35 as always. And I'll be available afterwards for a recitation section for an hour where you can ask questions on problem sets, problem set solutions, lectures, ideas, concepts, typos, etc. And if you see a typo, please bring it to my attention. You can email me with questions anytime, and I promise to get back to you within 24 hours. So you can email me a question anytime throughout the week, weekends included. Finally, I think a ruler is useful because there are lots of times when we're going to be drawing objects, and it's just a good habit to get into. Okay, so let's start lecture 4. So we were talking about the inverse of a matrix last time in lecture 5. So in particular, we were looking at the question of what do we mean by the inverse of a matrix? How do we calculate the inverse of the matrix? And why do we need it? So one at a time. What do we mean by the inverse of a matrix? And we discussed that last lecture. So again, if you're catching up, I advise you to go back to lecture 1 and master those concepts and applications, and then lecture 2, and then eventually lecture 3. Second question we want to ask, we asked this question last time, how do we find the inverse of a matrix? And again, we looked at that last lecture. And for a matrix of order 2, that's a square matrix, it has 2 rows and 2 columns, excuse me, for the generic form, we discovered explicitly by just brute force, which in this case was not too bad, that the determinant of a 2x2 matrix can be written as follows. You see there's a nice simple rule here. You take the A and D, the diagonal matrix elements, and you interchange them. And then the off diagonal matrix elements, you just multiply by -1. And you multiply that, you pre-multiply that by 1 over the determinant of the original matrix. Okay, next question. Why do we need the inverse of a matrix? Why is that even a useful thing to worry about? And what we're doing now, we're in the process of developing tools. And a lot of these tools we're going to use much later in the course. So rather than waiting to applications, let's figure out these tools now. Taking the transpose of a matrix, taking the inverse of a matrix, multiplying matrices. These are fundamental tools that you have to be fluent with. It's like learning a new language. Okay, so the fourth question is, what happens? So we didn't talk about this last time. What if your matrix A is of order 3 by 3, or of order 3 rows and 3 columns, or larger? We didn't attempt to try to figure that out by brute force, because that would be formidable. So we are going to come up with a nice scheme where we can calculate the inverse of large matrices. Note, we can only calculate the inverse of a matrix if it's square. So that's why we're referring to looking at problems where the matrix is of a particular order. So in order to find the inverse of large matrices, we're going to have to introduce something called an elementary matrix. So, and in fact, I'll say this now, elementary matrices are really another way to look at elementary row operations that we've talked about. So let's look at an example. Let's take a simple example. Suppose I have a matrix B that has 1 row and 1 column. It's a matrix of order 2. And suppose I want to apply the following set of elementary row operations to this matrix. In particular, suppose I just want to take a Xerox, I want to take row 2 in effect, and just multiply it by -3. So I'll get a new matrix. That'll look like that. And this new matrix I'll call C. So the question I want to ask is, if you give me B, the matrix B, and you want to turn it into a new matrix C, which is this, is there a 2x2 matrix that you could come up with that will make this equation true? And note the rules of matrix multiplication. All these matrices have to be compatible. So this question mark matrix has to be a matrix of order 2. It has to have 2 rows and 2 columns. So the answer is yes, there is such a matrix that you could build. What you need to do as a hint is start out with the identity matrix of order 2. So we just write this down. These matrices, matrix multiplication is compatible for all these cases. But this is a matrix B and this is a matrix C. Now, if you do the matrix multiplication, this is not correct. This is not going to give you, doing this is not going to give you this. But this is a start. And if you want to get C, then the correct thing to think about is simply to replace this 2-2 matrix element by -3. And that does it. So this matrix is very special. We'll call it capital E sub 1, and is an example of something called an elementary matrix. In other words, if you take this elementary matrix E sub 1 and multiply it by the matrix B, you will get the matrix C. So elementary matrices serve the same role as elementary row operations. They are the matrix manifestation of an elementary row operation. And again, how did I get this elementary matrix? Well, I gave you a hint. I start with the identity matrix of the appropriate order, in this case, order 2, and I have to fiddle with it. And in this particular case, to turn row 2 into a new row that's multiplied by -3, what I needed to do was just replace the 2-2 matrix element 1 by -3. Okay, so let's go through another example. So here's another example where we'll learn about elementary matrices. So let's pick a slightly more complicated case here. Let's pick a matrix of order 3. So it's square. That means by definition, it has 2 rows and 2 columns. And let us do the following set of elementary row operations to this matrix C. Let's take a Xerox copy of row 3, multiply her by the number 3, and then add that result to row 1. So you'll get a new matrix. First row will be this. Second row will be this. Third row will be this. And let's call this new matrix D. So elementary matrices allow you to, in fact, instead of looking at explicit elementary row operations, it allows you to solve the problem just using matrix multiplication. In other words, we want to find an elementary matrix, let's call it E sub 2, such that when you multiply it by C, you get D. So again, C is going to be a matrix of order 2. Sorry, E sub 2 is going to be a matrix of order 3. C is a matrix of order 3. Here's what it is, explicitly. And D is our desired matrix, which again is of order 3, 3 rows and 3 columns. So the question is, what is this new matrix, which we'll call it E sub 2? What's this elementary matrix such that when you multiply it, left multiply matrix C by E sub 2, you get the matrix D? Well, again, I gave you a hint before. Let's do it again. To get an elementary matrix, They're relatively simple. You start out with the identity matrix of order 1, or sorry, order 3. Diagonal matrix elements are 1, but the order of this matrix is 3. And you have to fiddle with this guy. So you have to ask yourself, what do you need to do to change this identity matrix into a matrix such that when you take this guy, multiply it by C, you get the matrix D. So think about what the elementary row operations are that you want. You want to take a Xerox copy of row 3, multiply it by 3, and add that result to 1. So that might suggest the following, that the way you fiddle with E sub 2 is that you take a copy of row sub 3, multiply it by 3, and then add that to row 1. And so in that case, all you want to do is make this guy 3, and that is correct. That's the right thing you want to do. So E sub 2 times the matrix C will give you the matrix D. So we have defined another example of an elementary matrix here. So you will have lots of practice, probably about 4 exercises in problem set 4, where you will be asked to write down the elementary matrix or elementary matrices for a set of problems. And again, the hint is you always start with the identity matrix of the correct order, and then you fiddle with it. But this fiddle technique is going to be a lot more clear, because all you're going to do is just take the elementary row operations you want to do and bake them into the elementary matrix. For example, here, you wanted to take, in this previous example, you wanted to take a Xerox copy of row 3, multiply it by the number 3, and add that result to row 1. Well, if you started out with the elementary matrix, identity matrix of order 3, you just multiply row 3 by the number 3 and add that result to row 1. This is exactly what you would get. Okay, so we are now ready to deal with the task at hand. How do we compute the inverse of a matrix where it's of any order, 5, 15, 1,000, 4? Okay. And there's a procedure we're going to use, which we will come up with a formula for, and it's based on elementary matrices. And then we'll go through some examples of how this works. Okay, so let's start. So suppose you're walking down the street and you come across a square n by n matrix A. So you're given this matrix A, and suppose you have discovered a set of elementary matrices. And it could be 2, it could be 30, it could be 1 billion. So let's call these E sub 1, E sub 2, E sub 3, and this goes all the way up to E sub K. So there's a finite set, but you don't know whether it's 3 or 13. So we're solving this problem in general. So what do these elementary matrices do? Well, you start out with your matrix A, and you left multiply A by these elementary matrices, all of them, such that at the end of the day, you get the identity matrix. So these elementary matrices have a very unique and important property as specified in equation 1. When you left multiply them all by A, when you left multiply A by all of them, you get the identity matrix. All right, the next thing we want to do is define a new matrix. So let us define a new matrix. And let's call this new matrix B. Where B is simply the product of my elementary matrices. And again, I don't know how many of these I needed to satisfy one, so that's why I just write it in the most general form. So given B, it follows that I can take the inverse of B. And based on our discussions last lecture, I know how to take the inverse of the product of matrices. It's just the inverse of elementary matrix 1 times the inverse of elementary matrix 2, dot, 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 times the inverse of elementary matrix K minus 1 times the inverse of the elementary matrix K. All right, so far so good. Next, let us combine equations 1 and 3 to get a new equation 4. And that's simply going to be that the matrix B times the matrix A equals the identity matrix, where all these matrices are compatible for matrix multiplication. Or again, since we know how to deal with the properties, we know all the properties of taking the inverse of a matrix, you can explicitly solve for A by just taking the inverse of B and left multiplying both sides of the equation 4 to get 5. Finally, if you use equation 3, equation 5 can be recast as the matrix A equals the inverse of E sub 1 times the inverse of E sub 2. Again, E sub 1, E sub 2 are just elementary matrices. And this goes on all the way up to the inverse of E sub K minus 1 and the inverse of E sub K1 multiplied by the identity matrix. Okay, so we're almost home. Given equation 6, can you come up with a nice compact formula for the inverse of your matrix A, of any matrix A? And the answer is yes. Just using the rules of properties of taking the inverse of the matrix, if I know from equation 6 what A is, I can calculate its inverse by just taking the inverse of what's on the right-hand side of equation 6. And again, making sure we understand the properties of how to take the inverse of a product of matrices, that just reduces to this. Okay, so you may not believe me, but we have solved the problem. We just have to step back, take a deep breath, and recognize that we've solved the problem. What do we want to do in this exercise? We want to find the inverse of a matrix A. So in order to find the inverse of the matrix A, we need a set of elementary matrices. E sub K, E sub K minus 1, all the way up to E sub 1. And we can get those guys from just going back to equation 1. Let's write down equation 1 first, then we'll look at what it means in a minute. Equation 1 says you need to take A, your original matrix, figure out elementary matrices, E sub 1, E sub 2, dot, 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 all the way to E sub K. Could be 10 of these, could be 3 of these, such that when you're finished, you get the identity matrix. Next, we use equation 7, which again I'll rewrite. Equation 7 says that the inverse of A is the product of these elementary matrices in this order. Remember, matrix multiplication in general is not commutative. So the order of the matrix multiplication is important. But now that you know what these elementary matrices are, you can use them, multiply them by the identity matrix, and that will give you the inverse of A. So there are two things that you need to do. First thing you need to do is figure out what the elementary row operation, the elementary matrices are that'll turn A into the identity matrix. And the second thing you need to do is take those elementary matrices and then in that proper order, multiply them by the identity matrix. And that should give you the inverse of A. Now, the beautiful thing here is to recognize that we can do these two steps. We can do these two steps at the same time and save ourselves a lot of work by constructing or building an augmented matrix. We know about augmented matrices from the first 3 lectures. And the augmented matrix we're going to build will be the matrix A glued to the identity matrix of the appropriate order. And then applying the necessary elementary matrices to this new augmented matrix so that we can get, we'll turn the A that's on the left-hand vertical bar into the identity matrix, and the matrix, the identity matrix that's on the right-hand side of that bar, we'll turn that to the inverse of A. And we have our answer. Our answer will just be that. It will be this guy. Okay, so let's go through an example, see how all this works. So let's pick a simple example. Let's pick a matrix of order 2. So you're given this matrix and you are asked to find its inverse. Now you could use that formula we pointed out earlier in today's lecture, or the one from lecture 3, but we're going to use the method we just described. So what's the first thing you should do? So let's do this in steps. First thing you need to do is build an augmented matrix where you take the matrix A. Oh, let's clean this up a bit. This is 3. and you glue it to the identity matrix of the right of the appropriate order. So A is a square matrix of order 2. The identity matrix has to be of order 2. So that's what the augmented matrix looks like. The next thing you need to do is apply elementary matrices to this problem. But as we pointed out, an elementary matrix really is a representation of an elementary row operation. So in practice, in actually solving this problem, we've proven that this conclusion works. But if you actually want to roll up your sleeves and actually get into the nitty-gritty of solving the problem, you want to just apply elementary row operations to this entire new augmented matrix, this 2x4 augmented matrix. And then when you finish, you want to have a result that looks like that. And you can just read off of that the inverse of A. I don't really need these parentheses. Okay, so let's do that in this problem. So again, the augmented matrix is going to be a 2x4 matrix, and it looks like this. And the goal is to take this thing to the left hand of the vertical bar and turn it into an identity matrix using elementary row operations. This is Gauss-Jordan elimination in a way, revisited. So take row 1, divide her by 2, and you get a new matrix whose first row looks like 1, 2, minus 1, 0. Note that you have to apply the elementary row operation to the entire row. The second row is not changed at all. What should you do next? Well, I'd like to turn this 2-1 matrix element into 0. So the way to do that is to take a Xerox copy of row 1, multiply it by minus 1, and add that to row 2. And the first row does not change at all. But the second row, after you apply this set of elementary row operations, becomes that. So again, the goal is to turn this creature to the left of the vertical bar into an identity matrix. So you can see that the last and final thing you want to do is just take a Xerox copy of row 2, multiply it by minus 2, and add that to row 1. Because after all, you want to turn this 1, 2 matrix element into 0. And if you do that, you'll get the following. Sorry, a little sloppy. And the claim now is we're finished. We've done what we're supposed to do. We've proven that this guy, we've written this in terms of the identity matrix. So our procedure tells me that what we're left with here on the right-hand side of the vertical bar is the identity matrix of A. So that's our answer. And again, it's of the same order. It's of order 2. Okay, so when you do this, a problem like this or any other problem, you need to check this to see if you've got the right answer. It's perfectly possible to make an error in arithmetic or transcription. So one of the things you should pay attention to is when you solve these problems, you need to do them slowly and carefully, either matrix multiplication or Gauss-Jordan elimination, or finding the inverse of the matrix. Okay, so let's prove this. So my original matrix was of order 2. There are its rows. And I claim I have calculated the inverse of A. So I need to figure out what this is. So matrix multiplication tells me I take the first row of the first matrix and I multiply it by the first column of the second matrix. So the 1, 1 matrix element of my result would be 2 times 3/2 plus 4 times minus 1/2. And the 2, 1 matrix element will be 3/2 minus 3/2. The 1, 2 matrix element will be 2 times minus 2 plus 4. And the 2, 2 matrix element will be 2 times 1 plus 3. So if you expand this out carefully, you'll discover that the 1, 1 matrix element is just 3 minus 2, or 1. The other 3 matrix elements are as follows. And in fact, you have calculated the inverse of A correctly using this procedure. I leave it up to you to similarly show that if you take the inverse of A and multiply it by the original matrix A, you also get the identity matrix. So that's something that I leave up to you to do. Okay, so we picked a relatively simple example, but the power of this approach can be gleaned by looking at more complicated matrices or bigger matrices, where you would not want to do this by brute force. So in problem set 4, I've given you ample cases of practicing this technique. And again, it's meant as a way for you to master your skills in matrix multiplication, Gauss-Jordan elimination, and really arithmetic and carefully transposing numbers. If you don't do this correctly, you just make one little subtle mistake, which I have done in either a sign or arithmetic or transposing a number, you will not get the correct answer. That's the bad news. The good news, you can always convince yourself you made a mistake by going back, taking the matrix that you think you have an inverse for, and verifying that that identity is true. Okay, so let's find the inverse of this matrix A. First thing you do is build an augmented matrix where you glue the matrix A to an identity matrix of order 3. So you get a new matrix, which is 3 by 6. And you want to essentially find the correct number or the right number, or just find the necessary elementary row operations that'll turn this object to the left of the vertical bar into the identity matrix. So let's get started. And there are lots of ways you can do this, but at the end, you should all get the same result. So what I'm going to do in this example is I'm going to interchange row 1 and row 2. That clearly is an elementary row operation, which is allowed. The first row becomes -1, 1, 3, 0, 1, 0. The second row is 2, 0, 1, 1, 0, 0. And the third row is left alone. I did nothing to this. Now you can see why I'm doing this, because now I want to turn this matrix element into 1. I want to turn the 1, 1 matrix element into 1. And that's one step towards turning this thing to the left of the vertical bar into the identity matrix. So the simple thing to do is just multiply row 1 by -1. And then you get 1 minus 1 minus 3. Again, you need to go through these steps very carefully and slowly. You make one error in sign, it'll screw everything up. But again, at the end of the day, you'll know that you made a mistake, and you have to go back and track and find where you made the mistake. And lots of times when you look at your final result, you can sort of tell, well, where you made a mistake. But you're not going to get this unless you go through many, many examples. Okay, what's next? Let's turn the 2, 1 matrix element into 0. So the way to do that is to take a Xerox copy of row 1, multiply her by -2, and add the result to row 2. Again, row 1 never changes. I just take a Xerox copy of it, so it's not altered. Still 1 minus 1 minus 3, 0 minus 1, 0. Row 2 is changed. Okay. It becomes 0, 2, 7, 1, 2. So I have a new 3 by 6 matrix, and the third row is left alone. It's not changed at all. What are we doing? We're trying to turn this object to the left of the vertical bar into the identity matrix of order 3. That's all we're trying to do. Well, I would tackle this let's call it this matrix element in the second row, second column. I'd like to turn this into 1. So there's an easy way to do that. I take my 3 by 6 augmented matrix in this form and just take row 2 and divide it by 2. So I'll get a new matrix. First row is not changed. 1 minus 1 minus 3, 0 minus 1, 0. Second row is changed. She becomes 0, a half, 7 halves, 1 half, 1, 0. The third row was never involved at all in any of these exercises. Okay. And I said I can make a mistake, and I just did. That's 1. Okay. So I take row 2 and divide by 2. 2 by 2 divided by 2 is 1. 7 halves, 1 half, and then 1. So I'm on my way to getting the identity matrix. What do I need to do next? Well, I want to get rid of this minus 2. I want to turn the matrix element in the third row and second column, I want to turn that into 0. So the way to do that is to take a Xerox copy of row 2, multiply it by the number 2, and add that to row 3. So what should I get? So if what we're doing looks familiar to our exercises that we looked at with Gauss-Jordan elimination, it should. We're using, in a sense, the techniques of Gauss-Jordan elimination, or we're using elementary row operations. So the first row does not change at all. 1 minus 1 minus 3, put my vertical bar in there, 0 minus 1, 0. The second row does not change. It's 0, 1, 7 halves, 1 half, 1, 0. Let me just say something that some people write 7 this way. Americans typically do. Europeans put a bar in it. And I think that's a useful trick to do, because some people, their penmanship, you might confuse 7 with 2, which is bad. And let's see, where are we? Well, we get a new row 3 in my 3 by 6 augmented matrix. He is 0, 0, 8, 1, 2, 1. Okay, you see what's going next. I want to turn this matrix element in the third row and third column into 1. So I just divide row 3 by 8. Nothing happens to row 1. So it's just a transcription problem. Nothing happens to row 2, but you got to transcribe these numbers correctly. And row 3 becomes 0, 0, 1, 1 over 8, 1 over 4, 1 over 8. You can see a pattern. What's appearing on the left-hand side of the vertical bar is starting to appear more. It's becoming simpler. And what's appearing on the right-hand side of the vertical bar is becoming more complicated. Okay, the next thing is to turn the matrix element in the second row and third column into 0. So a way to do that is to take a Xerox copy of row 3, multiply it by minus 7 over 2, and add that result to row 2. So you'll get a new 3x6 matrix. First row is not changed at all. Second row becomes 0, 1, 0, 1 over 16, 1 over 8, minus 7 over 16. And the third and final row was never changed at all. So we're getting there, we're getting there. And trust me, if you try to do this problem using brute force, it's much more work, far more laborious. Okay, what's next? That matrix element in the first row and the third column, you need to turn this into 0. Again, the idea is to turn everything into the left-hand side of the vertical bar into an identity matrix. So you're almost there. Take a Xerox copy of row 3, multiply it by the number 3 or scalar 3. We'll introduce that terminology next lecture, or a few more lectures, and add that to row 1. And so what that gives you is 1 minus 1, 0, 3/8 minus 1/4, and 3/8 for our new first row. But the second row is the same, and the third row is not changed at all. Okay, we're almost home. I need to change this matrix element in the first row and the second column to 0. If I do that, then on the left-hand side, I will have the identity matrix of order 3. So a simple way to do that is take the Xerox copy of row 2, add it to row 1. I go from left to right, and I will get 1, 0, 0, 7 over 16, minus 1 over 8, minus 1 over 16 as my first row. Second row is still the same. It was never involved in any of the elementary row operations in terms of a replacement. I just took a Xerox copy of row 2. I didn't change row 2, and row 3 was left alone. So what this process tells us is that I have to the left of this vertical bar the identity matrix. So what's to the right of the vertical bar? This thing must be the inverse of A. And just let's write it out. First row looks like this. Second row looks like this. And the third and final row looks like this. So it's a matrix of order 3. It has 3 rows, and it has 3 columns. And what we need to do next is ask ourselves, well, is this the right answer? Namely, is this expression true? If you take the inverse of A and multiply it by A, you get the identity matrix. Or and, is this expression true? So we have to go through the exercise of, in fact, verifying that these two expressions are indeed valid. So we're going to take a 5-minute pause in about a minute, where you can get up and stretch your legs. And the goal is to actually tackle this first. And I think we'll have enough time to actually tackle this second. And this is a very useful exercise to do, because it's going to, again, show you or prove to yourselves that you've mastered matrix multiplication. But again, you have to be careful in terms of the arithmetic, and you have to be careful in terms of transcribing the numbers correctly. So it is 2:50. Let's take a break, and we'll reconvene at 2:55. Okay. So let's resume where we left off last time. So we have a matrix A that we claim we know its inverse of. So we want to ask the question, if I take the inverse of A and left multiply A by it, again, I always have to use this distinction between left multiplying and right multiplying as far as matrices is concerned, because matrix multiplication is not commutative. A times B, if they're matrices, does not necessarily equal B times A. For numbers, that's true, but not for matrices. So is this true? Okay, so let's write this whole thing up. Here's the inverse of A, here's A. And the inverse of A, we're going to get into all the details. Here's the first row. Here's the second row. And here's the third row. And now I can easily write down A itself, because it doesn't have those fractions, 2, 0, 1, minus 1, 1, 3, and 0, minus 2, 1. Let's call this product a new matrix. Let's call it C. So C is going to be a matrix of order 3, according to the rules of matrix multiplication, and it's going to have 9 matrix elements. And so let's figure out what they are. So C11 is what you get when you multiply the first row of the first matrix by the first column of the second matrix. And as far as the first row is concerned, you have the following matrix elements. And each one of these gets multiplied by the respective matrix elements from the first column of the second matrix. So if you multiply this out, you get 7/8. This is when I told you about transcription errors, this is a 1/8. So I get 7/8 plus 1/8 plus 0 equals 1. Now to get the C12 matrix element, again, the rows in the first matrix are the same. The matrix elements in the rows of in the first row are still the same. So I can just repeat them. It's just that I'm looking now at the second column in the second matrix, and its matrix elements are completely different. So I read them off carefully. And here I get 0 minus 1/8 plus 1/8, and that's 0. And finally, again, regarding the first matrix, just looking at the first row, those 3 matrix elements are the same. The only thing that changes in this expression are the matrix elements of the third column of the second matrix. So they are 1, 3, and 1 respectively. Okay, so let's see, what does this give us? 7/16 minus 3/8, 1 minus 1/16. That's going to be 6/16 minus 3/8, and that vanishes. 3 down, 6 to go. To get this matrix element in C, I have to look at the second row of the first matrix and multiply it by the first column of the second matrix.
Now that it won't.
So can you please mute who's ever on there? Please mute yourself. So those matrix elements are 1 over 16, 1 over 8, and minus 7 over 16. And then I look at the first column of the second matrix, and the matrix elements are 2, minus 1, and 0. So let's do this carefully. It's 1 over 8, minus 1 over 8, minus 0. So that matrix element vanishes. C sub 2, 2. Again, the second row of the first matrix, those three matrix elements are the same. So I just have to copy them, transcribe them carefully. The matrix elements of the second column of the second matrix are different. They are 0, 1, and minus 2. So if I evaluate this, I get 1 over 8 plus 14 over 16. And if I do this arithmetic correctly, I get 1. Finally, the matrix element C sub 2, 3. Again, I'm still looking at the second row of the first matrix. So the matrix elements are still the same, but I'm looking at the third column of the second matrix. So I have a whole new set of matrix elements to worry about. 1, 3, minus 1. This comes out to be 1 over 16, 3/8, minus 7 over 16. That's going to give me minus 6 over 16 plus 6 over 16, and that vanishes. 6 down, 3 to go. I need to calculate C sub 3, 1. I need to look at the third row of the first matrix and pull off her matrix elements. They are 1 over 8, 1 over 4, and 1 over 8 respectively. And now I need to look at the matrix elements of the first column of the second matrix. They are 2, minus 1, and 0 respectively. Do the arithmetic, 2/8, minus 1/4, and this is going to give me 2 over 8 minus 2 over 8. So this matrix element vanishes. Again, if I want to evaluate this matrix element C sub 3, 2, I'm still looking at the third row of the first matrix. So the matrix elements for that do not change, but I have to look at the second column of the second matrix. There are new matrix elements. Here they are, just by inspection. Put a plus sign there. And this is going to give me 0 plus 1/4 minus 1/4. So that matrix element is going to vanish. And C sub 3, 3, again, I'm looking at the third row of the first matrix. Those matrix elements are unaltered, but I'm looking next at the third column of the second matrix, whole new set of data. Here they are respectively. So let's do this arithmetic carefully. Again, it's very easy to make an arithmetic mistake or a transcription error. So you have to be, it's worth your while to take the time to go through all of this carefully. So that's going to be 2/8 there, plus 3/4, and that's just 1/4 plus 3/4, and that's just 1. So if you go back and take all of these 9 matrix elements that you've calculated and put them back into the matrix C. C is a matrix of order 3. He has 3 rows and 3 columns. First row is 1, 0, 0. Second row is 0, 1, 0. Excuse me, the third row is 0, 0, 1. That is, in fact, the identity matrix. And so you've explicitly shown that the inverse of A times A equals the identity matrix. And again, you're going to have lots of practice with calculating the inverse of matrices and proving that, in fact, you've got the right answer in problem set 4. My only warning to you is do the problem slowly and carefully to avoid problems in arithmetic, which are possible, and to avoid problems in transcription. That just means copying the right numbers. Okay, so we're at it, so we might as well do this, right? Just because we've shown this is true doesn't mean we're finished. We have to also show that A times its inverse is 1, because matrices do not commute necessarily. Some might, but those are special cases. Okay, we know how to deal with this. We just have to set this up and work very carefully. We know what A is in our problem. It's a matrix of order 3. So it has 3 rows and 3 columns. Row 1 is 2, 0, 1. Row 2 is minus 1, 1, 3. Row 3 is 0, minus 2, 1. I have claimed that I have calculated the inverse of A, and I've claimed that I've done it correctly. Well, if my claim is true, then this operation had better give me the identity matrix also of order 3. So just because you prove this guy doesn't mean that you're finished. You have to prove that also. And the third row looks like the following. So what I'm going to do is call the product of these two matrices a new matrix. I'm going to call that new matrix D to distinguish it from what we did before. And I'm going to explicitly calculate all 9 matrix elements. So again, this is a exercise in matrix multiplication, which in my book is always a good thing. Matrix multiplication says take the first row of the first matrix and multiply it term by the first column of the second matrix. So first thing you're going to discern is 2, 0, 1 has to lie out there. Then I'm going to multiply this by 7 over 16 plus 1 over 1 over 6 plus times 1 over 16. And the final matrix element, I'm going to multiply that by an eighth. So this is going to come out to be 14 over 16 plus 1 over 8. And that's going to give me 16 over 16, which is 1. Again, the 1, 2 matrix element, I'm still sticking with the first row of the first matrix. So I have 2, 0, 1. But now I have to look at the second column of the second matrix. So the terms are different. Minus 1 over 8. Positive 1 over 8. Put a plus sign there. Positive 1 over 4. So this is going to give me minus 2 over 8 plus 0 plus 1 over 4. That's minus 1 over 4 plus 1 over 4. And that's 0. Trust me, you want to go through the detail and the diligence of spelling this out because you want to avoid arithmetic errors and transcription errors. Final matrix element, the first row of the first matrix is what's in play. So those guys never change, but you're looking at the third column of the second matrix. So you have a minus 1 over 16 plus 0 times minus 7 over 16 plus 1 times 1 over 8. This is going to be minus 2 over 16 plus 1 over 8. That's going to be minus 1 over 8 plus 1 over 8, and that's going to vanish. Okay, 2 down, 3 down, 6 to go. I need to now look at the second row of the first matrix and pull out its matrix elements, and they are minus 1, 1, and 3 respectively. And then I have to look at the first column of the second matrix and pull out its matrix elements. They are 7 over 16 plus 1 over 16 plus 3 times 1 over 8. So let's see, that's minus 7 over 16. That's plus 1 over 16. That's plus 3 over 8. That's going to give me minus 6 over 16 plus 6 over 16. So that matrix element is going to vanish. Again, sticking with the second row of the first matrix, these terms don't change. Those scalars don't change. But I'm looking at the second column of the second matrix. I have new data, minus 1 over 8 plus 1 times 1 over 8 plus 3 times 1 over 4. So I need to evaluate this. What am I going to get? 1 over 8 minus times minus plus 1 over 8 plus 3/4. That's going to be 2/8 plus 3/4. And that's going to give me 2/8 plus 6 over 8, which is just 1. The sixth matrix element, again, I stick with the second row of the first matrix. The minus 1, 1, and 3 do not change, but I have the third column of the second matrix. So that's new data. So that's minus 1 over 16. That's minus 7 over 16. And that's 3 times 1 over 8. Okay, so that's going to be 1 over 16 minus 7 over 16 plus 3/8. So that's going to simplify to 6 over 16 with a minus sign plus 6 over 16. So that's going to vanish. 6 down, 3 to go. I have to look at the third row of the first matrix. I can pull out its matrix elements. They are 0, minus 2, and 1. And next I have to look at the matrix elements of the first column of the second matrix. They are 7 over 16, 1 over 16, and 1/8 respectively. So this simplifies to the following, which you can see vanishes. The 3/2 matrix element, again, the third row of the first matrix, those matrix elements are the same. The second column of the second matrix, new data, minus 1 over 8 plus minus 2 times 1 over 8 plus 1 times 1 over 4. So that's going to be minus 2/8 plus 1/4. And that clearly is going to vanish. And the ninth and final matrix element, again, I'm looking at the third row of the first matrix. These three matrix elements are the same, but I have new data when I look at the third column of the third matrix. So I have minus 1 over 16 plus minus 7, minus 2 times minus 7 over 16 plus 1 times 1 over 8. So this is going to give me 0. It's going to give me plus 14 over 16. It's going to give me 1 over 8. And that's 14 over 16 plus 2 over 16. And that is 1. So if you take all this information, you take these 9 matrix elements, you can now reconstitute or build back D. She has 3 rows, 1, 0, 0, 0, 1, 0, 0, 0, 1, lo and behold, this is the identity matrix of order 3. And we have shown here that if you take A and multiply it by its inverse, you will get the identity matrix. Okay, so in problem set 4, which is online, it's available, you will have lots of examples and practice in looking at taking the inverse of a matrix, using the prescription we spelled out for 2 examples in today's lecture. You will also need to check in each one of these problems that in fact the following identity is true. Because this is a way to test that you have come home successfully. And you will also have examples, exercises, in dealing with elementary matrices, which we introduced as a formalism, but in practice, once we've learned what they mean, we don't really need to write them down explicit when we go through the mechanism of calculating the inverse of a matrix. Okay, so I want to say some final remarks about, I'll make some final remarks about the inverse of a matrix. Turns out it's going to be a very useful thing, as we'll see later on, to solve systems of linear equations. So if you will, it's the third method we've talked about so far in this course, if you want to solve a set of linear equations simultaneously. We've talked about Cramer's rule, but it has its limitations because it involves determinants. And it's also limited to the fact that it only applies for systems where the number of rows equals the number of columns. The number of unknowns is equal to the number of equations. We've found a way to get past that. Gauss-Jordan elimination. Gauss-Jordan elimination has 2 saving graces. It allows you to avoid determinants, and it also works for systems where you have m equations, but n unknowns. And that's a set of problems that you couldn't possibly solve using Cramer's rule. And I'll just say this, but we haven't talked about vectors. But we'll discover in a few lectures that you could write down the general form for a system of linear equations. It's a matrix A times a vector X, giving you a new vector B. And the way to solve this, again, this is a preview. So there's a glimpse of what the future looks like. If the matrix of A exists, if the inverse of the matrix A exists, then you could write down the solutions immediately. But we will see this. So this is not something we've talked about. We'll see this later. Okay, the second point I want to make is this is all good news. Let me tell you some bad news. Give you a cold dose of reality. Finding the inverse of a matrix is actually hard. On a computer. And folks sit up at night trying to figure out ways to solve problems in linear algebra without inverses of matrices. So I will give you, as in the problem set, a way to see this. You can go to Python. You have enough skills in Python where you could generate a 500 by 500 matrix that's random. So it has 500 rows, 500 columns, and you can make the matrix elements integers, you can make them real numbers, you can make them between 1,000 and minus 1,000. So this is really a random matrix. As I said in the problem set, it's really not a random matrix. It's a pseudo-random matrix for reasons beyond the scope of the course. But if you think about it, you can prove that to yourself. And you could actually use Python to time this calculation and see how long it takes Python to compute the inverse of a square matrix of order 500. Again, you would not want to take the inverse of a matrix that's not square, doesn't exist, at least at an elementary level. Okay. So third point is exactly what I just said. You can, and I'll put this in quotes, always find the inverse of the matrix. That's not true. You will see some examples in problem set 3. 4, where the matrix A is square. It's got to be square. Question I want to raise is, suppose you have a matrix that's not square. Suppose you have a matrix where the number of rows is greater than the number of columns. This is an example of what we talked about last time in lecture 3. This is an example of a tall matrix. And suppose you have a matrix where the number of columns is greater than the number of rows. That's the wide matrix. Turns out that even though these guys are not square, you can find something, I'll put it in quotes, the inverse of matrices B and C. But, and if you're interested, you can ask me, but it's really beyond the scope of this course. So it's really a sort of a advanced side. So I'm not going to worry about that, but I'll just mention that. Okay, so in summary, the inverse of the matrix is a very useful thing. We'll come back to that later. Excuse me. Turns out from a practical point of view, it's hard to calculate the inverse of the matrix on a computer. That looks kind of strange there, so let me clean that up. Avoid inverse. Well, strange is wrong. And there are special cases where it does make sense to take the inverse of a matrix that's not square. Okay, so let me again repeat what I said before at the beginning of today's lecture. I realize that a number of you are behind in terms of the course material. So let me make a recommendation what you should do. Problem set 1 the problem set solution key and lecture 1 are all available online now. And you should have the information where you need to access that. You need to go and look at problem set 1, do some problems in problem set 1, verify the solutions, and of course, go over lecture 1. So I would suggest in terms of order of operations, you probably want to look at lecture 1 first, then look at problem set 1, and then solve some problems. Make a fair-hearted attempt to solve some problems. Check the solutions, not by going backwards from the solutions, but trying some of the problems and looking at the solutions. When you think you're okay, if you get stuck, just cover with a piece of paper some of the solutions and just scroll down. I said this at the beginning of the lecture. The very first problem in problem set 1 is the hardest problem in the course. And I've actually outlined for you a way to do the third part, a third of it. So if you at least follow that, you'll be okay. And again, if you're behind, this is a way of catching up. You don't have to do necessarily all the problems in problem set 1, but you should make an effort to go back and do them eventually. Okay, same thing with problem set 2. It is available online. The solutions to problem set 2 are available online. And lecture 2, the video clip is available. So once you have finished lecture 1 and problem set 1, problem set 2, then and only then should you attempt to look at lecture 2. If you haven't seen it already, do that first, then go through problem set 2 and solutions. Again, with the same process. And all of this is available. Now, so you have some catching up to do. Problems, lecture 3 is available. I'll say a little bit more about that in a minute. Problem set 3, as well as problem set 3 solutions, they're all available. Turns out that one gentleman pointed out last time that there were some sound issues with the end of lecture 3. And so what's posted is partially, part of it is missing. So I will re-record this and get it replaced. And again, you don't tackle lecture 3 until you've tackled lecture 2, until you've tackled lecture 1. The course is cumulative. Finally, just for the record, lecture 4 will be recorded and posted sometime shortly within the next day or 2. And problem set 4 is actually posted. So what we've talked about today is posted, will be posted in terms of video clip, but the problem set is available. So you can actually, provided you've gone through problem sets 1, 2, and 3, start looking at this. Okay, so what I'm going to do now is stop recording. So just be patient.